Sure. Yeah. Okay. Yeah, my background's similar to a lot of your backgrounds, physics, electrical engineering. I worked in fusion energy research for most of my career, and been with MIT now 47 years. Though my status is actually an active retiree. I tried to retire 6 years ago, and then all of a sudden funding came through on this directed gyrotron drilling work, and I was roped into remaining involved in it for a while or longer. So anyhow, I'll talk about that and this talk. So let me share my screen. I have the view graphs here. Okay. Okay, can everybody see that now?
Yes.
Okay. Okay.
Before you start, I just want to tell everyone to mute your microphones, and so we don't get any interruptions again, please. Thank you.
Okay. All right. So later in my career at MIT, I got involved with working on geothermal energy. It actually was about 15 years ago when MIT started the Energy Initiative under a former president, Susan Hockfield, and Ernie Moniz was the first head of it. And one of the first things they did is they put out a report on needed technologies for various renewable energy sources. And under the geothermal category, the number one item of need was improved drilling technology. That was a bottleneck to accessing more geothermal energy. So my experiments in fusion and in our very high energy power sources to heat a plasma to over 100 million degrees. The idea came to me, well, why don't we apply one of these sources to melt and vaporize rock to penetrate a hole deep into the earth? And so I wrote a proposal to Ernie, and it went on from there. I did one study, then more, then we started attracting more money, Department of Energy. Now we have a big ARPA-E program with a spin-off company, and it goes on. So I'll describe that part of it in this talk. So first of all, an introduction, there's plenty of heat beneath our feet. There's 20 billion times the current global energy consumption of mankind present below our feet. This would be virtually a limitless source of energy. Just tapping 0.1% would supply all world energy needs for 20 million years. Currently, we're only scratching the very top surface. Only about 0.5% of our annual global energy needs is coming from geothermal energy. But if we can access deeper at less cost to greater than 10 kilometers, we could replace all fossil fuels for electric power generation. Now, this tremendous energy is not a resource. You can't consider it a resource unless you have the technology to access it. So I'm going to try to make an attempt to present a technology to help us get there. And primarily, I'm thinking about enhanced geothermal systems. These are systems where you drill where you have hot, dry rock. You don't have background water, like some of the current geothermal plants, like in the geysers, California area, where you have water present in high temperature near the surface. This is going anywhere on the surface and drilling deep enough to where it's hot enough, and then injecting water or another heat exchange fluid into the ground, and then flowing it through a heat exchanger that would have to be generated deep underground to heat it up, and then extracted by another well to a power plant. Now, everything on the surface of the diagram is exactly the same as a current fossil burning plant. We would have the same generator, the same transmission line connections. The only thing is we'd be replacing the coal burning plant or whatever by superheated water from deep underground. To realize this, we need advances in deep drilling, but we also need advances in heat transfer reservoir formation underground. Okay, deeper is better. Currently, this graph shows the depth from the surface as far as 30 kilometers under the surface. And the horizontal axis is temperature from 0 to 800 degrees centigrade. The blue trace is the average thermal gradient of heat increase for the planet, which is taken to be about 25 degrees centigrade here. Of course, it's hotter where the magma comes closer, like at geysers or near volcanic zones. But on average, for the whole planet, it's 25 degrees per kilometer. And so as we go down at 5 kilometers, the average temperature on the ground is about 150 degrees C. Then at 14 kilometers, the average temperature is at 374 degrees C. This is an important temperature point because this is a temperature at which water could be heated to be supercritical, temperature where current fossil burning power plants operate. And then as you continue at 20 kilometers, you can get to 520 degrees C. Now, the other curves I'm showing you here is the energy density per volume of underground rock as you get deeper. That energy density also increases significantly from about, if you use a unit of 10 to the 9 joules of energy. Now, that energy is equivalent to 278 kilowatt hour. And then another step to understand this unit of energy, it's equal to about 4 Tesla Model 3 charges, okay, an automobile. So you charge a car 4 times and you'll have 10 to the 9 joules of energy. And that increases, so the volume increases from about 1 cubic meter at 5 kilometer depth to only 0.4 cubic meter at 20 kilometer depth. And then the third curve here is the Carnot efficiency. That's the theoretical maximum efficiency for converting heat to mechanical energy or to run a turbine to produce electricity. So the important thing here at supercritical temperatures, 14 kilometer depth on average for the planet, we can get over 50% theoretical efficiency. So the motivation to go deeper is we would have higher temperature anywhere, practically anywhere on the surface of the Earth. So we can locate the plant near locations that are densely populated. We have a higher energy density, so that reduces the volume you need to generate a heat transfer reservoir, which eases that part of it. And you can have higher conversion efficiency, potentially over 50% conversion efficiency. Current mechanical drilling technology is a very old technology. It was first used in Pennsylvania oil fields in 1850s. It's over 150 years old. And so it's fully mature. No big breakthrough is going to happen, I don't believe, in that path of penetrating the Earth. And the mechanical drilling technology is particularly challenged by hard crystal rock formations like granite and basalt, which are the formations that we're trying to access, the hot rock. And drill rate decreases and costs increase exponentially with depth. The deepest borehole ever achieved was drilled in the Kola Peninsula in Russia during the Soviet Union times. It was 10.3 kilometers deep, and it actually took them 20 years and many starts and restarts to achieve. And it actually had the Cold War behind it for funding, so I don't know how much that cost, because there was kind of a race in the background who could go deeper back in the 60s and 70s. Um, we need a new approach, a completely new way to drilling, and that is to use directed energy drilling. This approach is not a mechanical grinding operation, but an energy matter interaction. There's no mechanical contact. Energy of a sufficient intensity will melt and vaporize matter. Matter can't stand up to intense energy. And we now have the means of generating the kind of energy in a way that could be applied to this environment. People were talking about drilling when the laser was invented in the 60s, but never really became practical. But we do now have the technology that could make it practical. The advantages of this are there's no temperature limit because we're operating at the vaporization temperature rock at 3,000 degrees C. There is no limit there. Greater depths because we're not impeded by the hardness of the rock, and faster rates are possible. Lower costs, as I will show. The drill rate could be constant and costs would increase approximately linearly with depth. And another benefit of drilling at these temperatures is that we could simultaneously make a casing, and the potential for depths much greater than 12 kilometers would be possible with much greater cost reduction. Now, the schematic of direct energy drilling operation at the point of operation is shown here. You'd have a waveguide, bring it in your high energy beam. It would diffract as it's launched because these millimeter wavelengths are somewhat long compared to the aperture. So you make a big hole, it would melt. There would be a standoff. The melt, some of it would be forced in the wall to make a casing, and then it would heat and vaporize the rock. Collinear with the beam is an intense gas purge to facilitate the quenching of the melt and blowing up the extraction as small particulate smoke. Millimeter are ideally suited for this application because the millimeter range between microwaves and infrared, it's a range where, I mean, if you have a modern car with adaptive cruise control, it operates at about 70 to 80 gigahertz frequency. And also 5G cell networks operate at 28 gigahertz coming into this range. This is ideal for borehole dimensions because it's long enough so small particulates don't block the transmission. It can look through smoke easily. And the wavelengths are short enough that they can be collimated as a beam in the dimension of a borehole of say 8 inches diameter. And the high temperature thermodynamics actually replaces a lot of the current functions done by drilling muds and mechanical drilling. The technology is available. Commercially, megawatt gyrotrons are now available. Waveguides for transmitting this radiation great distances, 10, 20 kilometers, are available. And we have remote diagnostics. You know, in the physics fusion development community, we were always monitoring a plasma medium at 100 to 200 million degrees. So monitoring a melt at 3,000 degrees is really nothing. All right, I'm going to go through the steps of the scientific basis. The energy requirements and the cost. It has to be economic or at least cheaper than mechanical drilling. Potential rates of penetration and borehole stabilization, self-casing. This slide's a little complicated, but I wanted to show the basic equation for the heat required to vaporize a rock. This equation was first published by Maurer in 1968 in his novel drilling technologies text, shortly after laser was discovered. And so he stated you need the heat to increase the initial temperature of the rock to the melt point times its heat capacity. This is an average quantity used here in this equation. Generally, this heat capacity changes with temperature, increasing with temperature. Then you need the energy of fusion, which is the energy needed to convert the solid state to a liquid. Then you need the energy to raise the melt to the vaporization temperature times the average heat capacity of the melt. Then finally, you need the heat to change the state from a liquid to a vapor, the heat of vaporization, the latent heat of vaporization. So actually, the numbers are available for most of these parameters, a little bit uncertain on the latent heat of vaporization, but for melting granite basalt, which are of interest here, the dominant type of rock deep underground is either granite or basalt. The melt temperature is on the order of 1,000 to 1,200 degrees centigrade, and the latent heat of vaporization is around 400 joules per gram. So to melt a granite basalt, you need 4 to 5 kilojoules per cubic centimeter. Then to vaporize it, the heat capacity, of course, is higher of the melt, and the melt temperature is somewhere over 3,000 degrees centigrade. The latent heat of vaporization is quite high. It's actually equal to the total energy needed to melt a rock, 4 to 5 kilojoules. So finally, you get to a number of about 25 to 28 kilojoules per cubic centimeter to vaporize granite basalt. Now, going back to my Tesla Model 3 comparison, a 10 centimeter cube of granite could be vaporized by one charge of a Tesla Model 3 energy. Okay, so the cost of vaporization can be calculated now that we know how much energy it takes to vaporize rock. We need to add to that the efficiency of our generation source on the order of 50%, the transmission line efficiency, and then the efficiency of the absorption of the melt by the rock, which I found in the lab to be about 70%. So you have to multiply the required heat that the rock has to absorb by the efficiency with which you can deliver to it, which is about a third. So on this graph, I'm plotting the cost per meter, actually per meter of, actually this should be a, yeah, okay, per cubic meter, I think. All right, so we go on a logarithmic scale from 1 to 100, and then we have a borehole diameter that varies from about 2 centimeters to 50 centimeters. 8 inches would be a typical size diameter that we would need. The blue curve is the amount of the cost per diameter to melt it, and then the red curve is the cost to totally vaporize that volume of rock. So okay, this is cost per meter for 8-inch diameters to vaporize. So the cost to vaporize or melt or vaporize falls in the range of $14 to $85 per meter of penetration. This is assuming a 12-cent per kilowatt hour cost. This is not the cost we're paid for with all the transmission costs and others added to it. So you would need to use, let's see, this is for 26 kilojoules per cubic centimeter centimeter and 4 kilojoules per cubic centimeter melt, which is the mean of the number range that I gave in the previous view graph. So for an 8 kilometer deep borehole, you need about $100,000 to $700,000 for the cost of electricity to open that hole. This is just the cost of the electricity, not other costs like labor and infrastructure or whatever, but just the main consumable in directed energy drilling. So that number, seems high, $700,000, but the current cost of a mechanical drilled well to 8 kilometers is on the order of $50 million. So this main consumable in our case is actually quite small to the total cost of current drilling. And don't forget, we can simultaneously case the hole which eliminates half the cost of a mechanical drilling hole. Going back to my Model 3 Tesla charges needed, you need between 4,000 to 25,000 charges of that battery pack to open 1 8-kilometer hole. Okay, so the rate of penetration, it's linear proportional to beam intensity. So I'm plotting on this graph the rate of penetration from 0 to 100 meters per hour, and the power density needed across the area of the borehole. And here I go from 0 to 100 kilowatts per square centimeter. So if we take an 8-inch diameter hole, the area of an 8-inch diameter hole, and apply 20 kilowatts per square centimeter. Now that's actually about a limit of what you can bring to bear at atmospheric pressure, because you'll have breakdown and a plasma created, which would limit us from going infinitely high in power density. But about 20 kilowatts per square centimeter should be possible. This would correspond to a drill rate of 19 to 40 meter per hour, depending on if you're just melting it and displacing the melt, or you're going all the way to the heat needed to vaporize it. 19 kilowatts, 19 meter per hour. So at 19 meter per hour, a 10 kilometer deep borehole could be drilled in just 22 days. So one of the deepest boreholes drilled in the U.S., the 9.5 kilometer deep Big Bertha Rogers Hole, Oklahoma, took 18 months to drill. Now, I'm assuming we're on 24/7 and we're not stopping to retract the waveguide or whatever. This is just a theoretical estimate of what the continuous on time would be needed for the source to drill. But that could be a tremendous savings in cost by drilling a hole much more quickly. Then the high temperature thermodynamics comes into play because we need to get rid of the drilling mud. A beam can't propagate drilling mud. And when I present this to the drilling people in the current fossil fueling drilling business, they're horrified with that. How can you drill a hole without drilling mud? Because the column weight of a column of mud stabilizes the hole, prevents it from collapse. But I like to show that the thermodynamics of high temperature drilling provides the stabilization pressure needed without any mud. Here I'm showing this plot, the depth from the surface to 20 kilometer depth, and then the subsurface pressure from atmospheric pressure 1 to over 5,000 atmospheres pressure. For an incompressible column of matter, like a column of rock or column of water, the lithostatic pressure increases as the red curve shows. At 20 kilometers, it's over 5,000 atmosphere of pressure. At 14 kilometers, it's 3,700 atmospheres pressure. For a column of water, the hydrostatic pressure, it's only 1,300 atmospheres at 14 kilometer depth. For an open borehole filled with gas, as we would need for directed energy drilling, the air is compressible, so the pressure scales as barometric pressure, and it follows this curve. I'm assuming for a gas-filled argon hole. And start at 150 atmospheres. So under these conditions, the barometric pressure would be equal to the hydrostatic pressure at 1,300 atmosphere. Okay, that's if we don't apply any heat. These are just the background pressures, but we're heating the borehole to 3,000 degrees centigrade in a confined volume. The real gas law, which includes a Z term for compressibility, says that if all things constant, and the volume is confined, pressure will scale with temperature. So the pressure at the point we're applying our heat can be increased far above the local hydrostatic or lithostatic pressure under high temperature drilling and stabilize the hole. And not only that, under such pressure, we could drive a low viscosity melt at near vaporization temperature into the wall to create our casing. If we displace all of that material into the wall, it would make a wall thickness about 5 times or 1/5 the diameter of the hole. With that thickness of a hole, the collapse strength of a tube approaches Young's modulus of the material of which that tube is made of. For basalt glass, the Young's modulus is about 85 gigapascals, 800,000 atmospheres. So not only could we stabilize the hole while the beam is on with high pressure, confined volume, high pressure, as the hole cools, it creates a tremendously strong liner, far stronger than any cement or steel casing currently used, that could continue to stabilize that hole long after you've drilled it. In addition, that high temperature, high strength casing is a glass. It can conduct a very high temperature fluid from underground, and we wouldn't be limited just 400 degrees centigrade. We could go to much higher fluid temperatures than any possible cement casing. So anyhow, so this is the scientific basis. So now the technology basis. Most of the technology spin off from fusion energy research. We have the high-power gyrotron sources, we have the millimeter transmission lines, and the remote diagnostics. I'll describe each in turn. This shows a couple of gyrotrons here. This is just a gyrotron tube that was built at the Japanese Atomic Energy Agency. And this is a 1 megawatt tube at 170 gigahertz. Basically, the way the gyrotron works is you generate a high voltage electron beam on the order of 90 kilovolts, and you transmit it through a resonance cavity inside a magnetic field. An interaction occurs due to electron cyclotron resonance. So this resonance is about 28 gigahertz per Tesla of magnetic field. So you would use 5 Tesla for 140 gigahertz. And it's actually a little more than that for 170 gigahertz. So these are superconducting magnets. And then 50% or more is converted to a millimeter beam. It's directed out of its waveguide by mirrors and out a diamond window out horizontally. And the spent beam then is collected by a big heat exchanger. You know, if you're generating a megawatt beam, there's a megawatt up here. So obviously the heat exchanger is much larger than the tube itself, which is the resonator cell, which is located down here. This is just a tube, but it sits in the magnet, and here is a tube at the D3D fusion facility at General Atomic in San Diego. It's a 1 megawatt tube at 110 gigahertz, and this is the cryogenic container, the superconducting magnet. You see the frost building up on one of the outlets, and the gyrotron window is up here, and this is their gigantic heat exchanger for the spent electron beam. ITER has 28 of these tubes on order for 24 megawatts of heating. GA has 6 these tubes for heating in their experiment. So we can efficiently transmit that power too in hollow overmoded waveguides. An overmoded waveguide is when the diameter is many times the wavelength. And in that kind of a waveguide, you can transmit a hybrid magnetic electric mode that's peak, like a Gaussian beam, which is the most efficient guided mode. And what happens at this overmoding is the electric field approaches zero to the wall. That's why they're so efficient. And to propagate this mode in the metal waveguide, you need to corrugate it with corrugations that are quarter lambda and about 3 per wavelength along the length. So they're very finely corrugated. These are commercially available middle range waveguides manufactured by General Atomics. You can see the corrugations. I think this is larger than 170 gigahertz corrugation. And the efficiency as well, by the way, that mode could be propagated to corrugated metal wall, but it's also the same mode propagated as smooth wall dielectric. It is the same mode used in the infrared in a hollow fiber optic to transmit infrared communications links tens of kilometers in distance. However, now we're scaling up to millimeter wavelengths, a factor 1,000, and the hollow core can go a factor 1,000, comparable to borehole dimensions. Here I'm plotting the transmission efficiency from 100% to 0.6 on the vertical axis, and distance, transmission distance from 0 to 20 kilometers. And for a copper corrugated waveguide, about 12.5 centimeters diameter, 5 inches, you could transmit 90% efficiency at 95 gigahertz to 20 kilometers. If you could use a more practical material for borehole, carbon steel, the conductivity is lower, but still you could transmit that beam to 20 kilometers with 70% efficiency. And this scales as wavelength squared over diameter cubed. Something like a 14% increase in diameter will double the distance to 40 kilometers. So you could go from 5.5 inches to say 6.5 inches. And on paper, at least, you can go 40 kilometers if you want, efficiently. Now, a dielectric, as I said, a dielectric counterpart of a fiber optic can also transmit this mode. You could, in a granite borehole, you could transmit having granite as your confinement material, or the vitrified granite, 20 centimeter diameter, about inches. You go 100 meters with 70% efficiency. So you could actually use the borehole itself that's created as a waveguide, say to make a short horizontal link to connect one vertical well for injection and another one for extraction down deep. One thing, these are the boundary losses for the beam in the waveguide, and we're assuming it's filled with a non-absorbing fill, like air at atmospheric pressure doesn't absorb anything. However, if you go to high pressure, molecules can have induced dipole moment, so you have to look at this more carefully for the pressures encountered deep underground. And also we have the diagnostics here. We use millimeter wave radiometers to measure temperature. We use millimeter wave reflectometers to measure position or rate of penetration. And we couple high frequency diagnostic into a lower frequency, high power gyrotron beam. In this case, it's a 28 gigahertz beam in my lab. And we can monitor the temperature and displacement in real time. And here's some data that I have from the lab where we melted granite. This scale is 0 to 2,500 degrees centigrade. So you could see when it melts at this discontinuous point, the melt goes opaque. This red curve, by the way, is a diode detector on the back of the rock to look at transmission. When you melt the rock, it becomes completely opaque, little transmission, and the temperature jumps tremendously. So we have achieved these high temperatures in the lab. And also the displacement, a coherent reflection will interfere coherently with the local oscillator. So you can see fringes as the reflection distance of the melt moves. So the 94 gigahertz in this example is showing 6 fringes. One fringe corresponds to displacement about of a quarter wavelength. So this is about 1 centimeter displacement that we observe. Because the coherent heating beam is also coherent. At 28 gigahertz, 3 times the frequency, we see 1/3 of the fringes in the reflection of the gyrotron beam. So that kind of confirms we're looking at the displacement. Here, the time scale is seconds. This occurred over about a 2-minute period. We displaced the rock 1 centimeter, but we're not vaporizing it here. I didn't have the power to vaporize the rock. I only had the power to melt it, and we're displacing it by the force of the collinear airflow that's blowing out the rock in this case. Okay, and I'm going to show the laboratory experiments. We're using 28 gigahertz because that's what I had in the lab and available at other labs. At MIT, I did experiments with a 10 kilowatt gyrotron where I could transmit about 5 kilowatt to the target. I didn't have as an efficient transmission line. And we achieved the first rock melts with hole depths that are just as deep as the diameter hole, namely 2 inches diameter bore holes. And then we moved on to Oak Ridge National Laboratory, where they have a 200 kilowatt gyrotron, where they could potentially deliver 100 kilowatts on target. But I'll show that didn't really work. We weren't going to try to do deeper holes than 3-inch diameters there. My early work was in partnership with Ken Oglesby in Impact Technology, and Quaise Energy was the lead organization here in the RPE supported ORNL work. So this is the experiment at MIT. We had a commercial gyrotron system from CPI. It's a company located in San Jose, California. And you could buy a 10 kilowatt system that's packaged with the gyrotron, the electronics, power electronics, all the control electronics. You just have this delivered and connect the electrical system and the water system for cooling, and you're set to go. The gyrotron is right here in this tiny drum-shaped object. This is a copper magnet because we're at low or frequency, and also this tube operated on a harmonic. We only needed half a Tesla field, so you could use a conventional copper magnet. And the beam is directed outward vertically. There are waveguide components for conditioning and monitoring this beam, then transmitted to a transmission line that then directs by a miter bend vertically downward. And up here, I had the diagnostics connected that I showed you earlier through this 3-inch diameter corrugated waveguide, then a taper, and then into a test chamber where we locate the rock. The test chamber is completely enclosed steel container, so all trapped radiation is confined. And we have our environmental safety office at MIT that comes with microwave sniffers to make sure there's no hazardous radiation leakage before we operate. And so the rocks are heated in here, and there's water cooling. We can monitor the heat that's not absorbed by the rock. This is how I've determined that the 70% is absorbed by the rock. So the other 30% is reflected. But as well, by the way, the gyrotron does not like reflected power. And that was a unique thing in the application of this technology to heating materials, because you do get a lot of reflection from a discontinuity between the gas medium into the material medium. In magnetic confinement fusion plasmas, we have a vacuum where we're transmitting the beam, and the plasma is 100% absorbing. So there's no reflective power problem in magnetic confinement fusion research. However, for these experiments, we had to develop a reflected power isolator, which was implemented up here. And that actually worked. We couldn't melt the rocks until that was in place. We implemented the forward gas purge, and we were able to make craters in the rock without vaporizing. We implemented the collinear high temperature diagnostic, which showed us we could monitor in real time the process. We also showed we could propagate in the borehole vitrified walls. I'm going to show you that in one test sample. And then we did observe the pressure rise in the confined volume once we added heat. We implemented the rock surface in a tight chamber with a very tiny escape orifice for the injected gas, and the pressure drop of that escape orifice gave us a confined volume simulating a deeper, longer borehole, and we did observe the temperature rise with heating, as the real gas law would tell us. Okay, so the laboratory boreholes. This shows a granite sample opposite our waveguide inside the test chamber after the test chamber was opened, and the waveguide outer diameter was 42 millimeters. The launch aperture was tapered down to 20 millimeters inside the waveguide there. But we made a 50 millimeter diameter hole. So that demonstrates that the beam diffracted as it was launched, as I told you. In fact, for this mode launch in this aperture, and the rock surface is located only about 1 inch below the waveguide, 25 millimeters. The beam opened up to 50 millimeters from a launch aperture, 20 millimeters. But notice this rock broken open. Notice that the hole is relatively straight. If this hole continued to propagate in air, it would be more than 100 millimeters in diameter. But what happened is you started to make the glass hole. It confined and collimated the beam to be straight. Okay, so we showed that we did have guiding in the vitrified wall. And you can also see, without any pressure behind the beam, this is all atmospheric pressure, we did develop a 4 millimeter thick vitrified wall. So we did show that we can launch a beam, melt a hole, the hole guides it, and the hole can be vitrified. And we did this with a power only 5 kilowatts. We have available 100 megawatt plus tubes. Imagine what we could do with that. Okay, so we went on to get to more power. We went to Oak Ridge National Laboratory. This is a 200 kilowatt, 28 gigahertz gyrotron they have there. This is an old tube built in the 1980s, and it was left over for outside people to propose experiments. So we arranged to use this tube. We were told it would operate well CW. Normally, magnetic confinement fusion experiments are short pulses on the order of seconds, but we wanted to operate this for an hour continuous. So we did go down there, but unfortunately we discovered that the gyrotron output was of poor beam quality. When we impacted our target, this was a 150 millimeter diameter, 6-inch diameter target. There's a basalt rock here embedded in a cement cylinder to hold it together. By the way, I didn't show that these rocks samples are held by steel bands in our lab, because we're at 2,500 degrees centigrade here, and up here at the edge, we're near room temperature, a tremendous thermal gradient. The rocks fracture thermally. Before we banded them, these rocks would flow apart like an explosive, as though you put a stick of TNT into them. Anyhow, so the small samples we do in the lab need to be confined, and that simulates this static pressure we'll find in the field. But notice the poor beam quality of this gyrotron. It came out like a blunderbuss. It's full of hots. There's no single collimated peak on center of the beam. It was very badly multimodal, is what we call it. And so we had an issue with this. It also caused breakdown issues in the waveguide, in the quarter waveguide. And after struggling using existing components, we couldn't really improve significantly. The best we got was up to 30 kilowatts for some tests. But we did achieve our goals of deeper holes. So now the work is transferring to Quay's energy facilities in Houston, where they're dedicating gyrotrons to this research and development, and they are setting up a 25 to 75 kilowatt 28 gigahertz tube with better mode converters to produce a clean beam. They also have a 100 kilowatt 95 gigahertz tube that they plan for initial field use. And there's a 1 megawatt 105 gigahertz gyrotron on order from CPI in California. This is a modern tube with modern mode converters. It'll be 98% clean mode when they get it. It also is a point in China, there's efforts starting out in a university laboratory research at Chengdu, China, have published the results similar to what I achieved at MIT with a 20 kilowatt, 45 gigahertz gyrotron out there. So there is works not only here, but elsewhere starting up on this. So commercialization, a company was formed a few years ago, Quaise Energy, to commercialize millimeter drilling gyrotrons. Initially, Alta Rock in Seattle, a geothermal company, and I proposed RP project was approved, but they decided that they needed to focus their business on conventional geothermal development and spun off Quaise Energy to develop the millimeter technology. So they're well lodged and pursuing this. The primary goal is to build super hot rock geothermal systems for electric power generation. If you go to their webpage, you can see their goal is to access supercritical steam, so he can bring back online existing abandoned fossil fuel plant, and so that's a goal. Because in a way, you could say our geothermal plants are already more than half built. All we have to do is bring in the deep wells where the old coal burning furnace was, and we will have a plant that's already connected to the grid producing power. So we're hopeful that can be achieved once we solved our engineering problems of coupling the beam to rock at high power. So summary, I hope I showed you that the science is optimum, the energy and costs are reasonable, great penetration rates are possible. The thermodynamics actually help us to build and stabilize these holes, and casing is a real possibility to reduce costs even further. Technology is commercially available. The main pieces of it, the gyrotrons, the waveguides, the diagnostics, all we have to do is complete the engineering to put these pieces together for a deep borehole. And the feasibility has already been shown in the lab, as I showed you the holes, and the commercialization is in progress. So with that, I'm open for questions.
Thank you very much, Paul. That was fantastic. You certainly have progressed. I have a tremendous amount of hope that this may work. But I do have, some obvious questions, which is no one knows what it's like to drill down that deep. For a start, do you anticipate any kind of changes in the kind of rock? I think recently they found that there was at some depth, or at least the deep hole seemed to be like an ocean down there with a rather soft and spongy rock. And I'm wondering how that would be affected by your...
That's a new frontier. You're right. We're going deeper than anybody's gone before. And they have commented about the plasticity down deep below. And so, that is a new question. But they do drill into plasticity environments, like in Hawaii, near the volcanoes. They have shallow wells that access the magma, and they actually use mechanical drills to drill into that. They put in a flowing fluids, water that cool that magnet temporarily to allow the penetration to continue. I know that it's a new frontier. You're right. I hope we'll be able to access it quickly, more cheaply, and explore it. But that's another thing that I guess will need to be explored and
Right.
developed. Yeah.
And my other thought is that I'm particularly interested in nuclear waste and the ability to drill deep holes and stuff the stuff down there. But it does still raise the question as to whether, can this stuff come back within, say, the next few thousand years
Yeah,
and
I
still
actually
contaminate?
worked on that a little bit because we did have one project with DOE about looking at plugging a hole. I mean, that's the weak link in deep borehole storage is the hole itself and how to plug it. We were looking at plugging it with melted rock. So we had mixed results on that. But actually, if you could go deep enough, the Earth's mantle is radioactive. That's what produces most of the heat in the core is the decay of long-lived radioactive isotopes. Actually, that would be a good place to put other radioactive waste into the.
So I guess in a way we're helping heat the Earth again. Okay, Albert, you had your hands up first. Can you unmute? Albert?
Yeah. Can you hear me now? Okay.
Yes.
Paul, very interesting presentation. In the beginning, you also talked about a heat exchanger reservoir in the bottom. You haven't told us anything about that and how easy is it to do that, to make sure that what you're putting in will heat up when you pull it out?
Yeah, currently the approach is to use fractured reservoirs to create a large surface area because the thermal conductivity of rock is very slow and you need many hundreds of square kilometers of surface area with the current approach. And that's still the mainstream. I kind of propose a different approach once we have gyrotron drilling demonstrated. As I mentioned, we could drill a horizontal hole to connect vertical wells. And I was looking at, if you drill a series of 15-kilometer deep holes and then interconnect them, it's possible you could put enough holes in there to make a new kind of heat transfer reservoir, sort of like an old-fashioned steam radiator in the building, where you flow it through a lot of long, smaller pipelines to heat it. If you the conductivity rock is very slow. The escaping thermal energy from Earth's surface is only about 65 milliwatts per square centimeter. It's a very slow conductive flow. If you look at solar energy impinging on your surface and averaging it over a 24-hour day, it impinges about 250 watts per square centimeter. So there's a great difference in thermal power flow between solar energy on the surface and thermal energy flow underground. But Fourier's law for solid heat transfer is the product of thermal conductivity and temperature gradient. And when I was looking at using many borehole walls, if you keep the fluid in the borehole flowing fast enough that you establish a large gradient between the rock and the heat transfer fluid. In one case, I was looking at keeping the fluid 25 degrees lower than the adjacent rock. Then it's possible to get maybe up to a megawatt from one deep borehole to 20 kilometers, because you can engineer or form the heat transfer part of the Fourier's equation to increase that thermal flow. And that would reduce the surface area needed overall. But you also have to go deep where you have a lot of energy available density so that field will continue to produce for a useful lifetime. So, Yeah, you need new approaches, but like gyrotron drilling is a completely new approach to drilling. I believe it may open up the possibilities of completely new approach of how we think about engineering a heat transfer reservoir.
Sounds good. And Quay's Energy, is that an MIT spinoff, or are you involved in it? Can you tell us something about that?
Well, I'm still involved in it as an active retiree on the MIT part. You know, Quay's has a partnership with MIT. MIT helped spin off Quay's Energy through the engine, and so they have their headquarters here at in Cambridge, and their facilities are down in Houston, Texas. So I do talk with them, and they do fund some research at MIT. I'm partly involved with them. I'm mostly retired though, but the Plasma Science and Fusion Center is planning to have a program doing supporting research on this technology and the microwave transmission components, diagnostics, and that part. And also the rock mechanics lab at MIT is involved in testing the strength of the vitrified rocks for possible casing.
Thank you.
Hugh.
Yes, thanks. Paul, that was really very interesting. Thanks. I've got a probably wildly premature economic question. Once one of these things is successfully in, which I recognize is a bit ahead of the game, do you have any sense of what the electricity that it might generate would cost? And the reason I ask that is one of the major expenses of the drilling is the cost of electricity. So maybe you can leapfrog these things, and only the first one that goes in is really expensive, and after that they support one another.
Well, I haven't really looked that far, but Quay's Energy might be able to answer their question because they are looking at economic issues of this down. I think presently it's expensive because the cost of the drilling is so enormous to get down to useful heat. And at the low temperatures you get within the top 6 kilometers, you have to use low temperature generators, the binary cycle and whatever, and the Canora efficiency is low, 20% or 3%. Right. So I think that is all related to not being able to get to deeper, higher energy temperatures currently, and hopefully once we do that, we'll reduce costs. But as far as trying to estimate what it'll ultimately be, I haven't really thought about that, but I'm sure somebody Quay's has.
Right. Because the economics often drive how much things.
Yes, that is critical. Yeah.
Thank you,
Michael.
One, this was rather amazing. Two, I think it's a disruptive technology, so I wonder where the pushback will come from. Three, I think it's kind of interesting that this fusion work that says, well, we can get a limitless supply of energy from water is interesting in that, well, we can get a limitless supply of energy from the land even quicker than continuing with fusion in the direction that it's going. Kind of find that funny. Sometimes you just stop, as an inventor, sometimes you stop in your path and you say, wait, I'm on the wrong track. I've got to go in a different direction, even though I have to turn 90 degrees. And I think this is interesting in that respect. I would ask, I saw that there's a flushing gas, a purging gas that's used. Does that gas come out at the surface in a heated form? And if it comes out heated, are you capturing the energy to generate electricity with that heat? Or is that used again in the process itself?
Well,
the last part of that question is there a limit once you drill the well? Is there a limit to how much you can extract for some reason?
Well, I don't think there's a limit. The gas that we purge would be a much higher volume than the gas that we ablate from the rock at least 3 times or something on that order. So that purge flow is needed to quench the ablation, because we can't extract a melt or a vapor that's hot, because it will condense on the walls of the borehole higher on the waveguide. So the purge is first to keep the waveguide cool and clean, then to purge the vapors from the rock. There's a standoff distance in that diagram from the aperture to launch waveguide and the rock, that may be a meter or 10 meters or whatever. In that transition region, the temperature's got to come down from 3,000 to under 1,000 by the time it gets to the waveguide. And then the hope is the particles will be quenched fast enough to be nanoparticle size. I was looking into this in the literature. The only thing I could find was stony meteor burn up in the atmosphere. And there were studies down that a rocky meteor in the air will vaporize, and the average size of the particulate would be around 6 nanometers on one study that I read in the 80s. So we're hoping to reproduce that by having a large enough quench volume that will quench the ablation into nanometer-sized particles, and the velocity would also be strong enough in that annulus to carry all of that up to the surface. By the time it gets to the surface, I don't think it will be very hot, but we do need to handle the pollution it's bringing up in the nanoparticles. That's a hazard in itself. I had to go through with MIT Environmental Services about the potential making nanoparticles. So we had our exhaust not only goes through a HEPA filter, but then through a container of water. We bubble it through to scrub particles. So something similar would have to be implemented on the surface for the exhausted gas. It would have to go through some filtering, maybe bubble through a pond to collect the particulate from the extracted particulate from the borehole.
Mm-hmm. Thank you.
Actually, that does raise an interesting question about environmental impacts of this technology. Actually, there are several aspects that just spring to my mind. One is the material that you actually bring up. It's a bit like mining. So one could think about using it in terms of mines, but you probably will have as well not just simply contaminants, but potentially useful material from that drilling. And I wonder if that could be filtered out as well.
By far
heavier metals must be down there.
Highest fraction of the small particulate will be silicon dioxide. That's a precursor to making electronic circuits. Okay, there's a market for nanoparticle silicon dioxide. In fact, when I first wrote about this back in 2009, 2010, I had some scientists from Moscow contacting me about whether we could commercialize the nanoparticles being extracted for the electronics industry. Of course, there'll be other stuff you'd have to filter out, but there could be potential. It would be nice if we could extract the nanoparticles, collect them, and then sell them.
Yeah, I must admit, when I first heard of your technology, I did a little calculation of my own, and actually came up very close to the drilling rates that you have there. But one of the interesting things, though, is could this also be used, for example, instead of our old-fashioned mining techniques? Rather than developing, maybe it's on too small a scale just to drill a hole, but could it also be used, though, to melt rock and to create basically a mining infrastructure that's very different from that today?
There's potential application for extraction. I had engineers from South African gold mining contact me. When they mine gold in granite formations about 4 kilometers under earth there, they have whole cities of people. They have, 3,000, 4,000 people working underground. And in order to break up the rock to get more granite to find the gold, they use explosives. So when they do that, they bore a lot of small holes, put dynamite in, then they evacuate the small town. They have their explosion. Then it takes some weeks before they can go back in there to clear the chemical exhaust, whatever. And the engineer said, do you have a non-chemical way of breaking up rock? And I said, sure. Our basalt samples split apart, so there's potential. You could use an electromagnetic beam locally to heat high, and then you break larger volumes by the thermal stress potential.
Here's another thought though, because you're producing nanoparticles, essentially, if you use a centrifuge, could you also then spin out the gold? And
well, I don't know. For producing nanoparticles, vaporized rock, you don't want to use that energy. But to heat to a couple thousand degrees, you need a fraction of the energy to melt,
right?
Create the thermal stress to break up rocks. I'm just saying it could be a tool to help mining and rock extraction, but not to melt and create nanoparticles, because that could only happen on a small volume at a great expense. But by using the thermal stress as an energy at lower costs as a substitute for chemical explosion, so that may be an application there. We have talked about that. Yeah.
I think one of the interesting aspects is that you are utilizing even current infrastructure to be able to once you drill the hole, essentially you're just delivering heat. You mentioned that there would be potentially other heat exchanging material, liquids. Do you have any idea what that'd be, like CO2 or something?
Water is the most common heat exchange fluid, but people talk about CO2, supercritical CO2 as a possible heat exchanger.
Right.
So there might be other fluids, but water is certainly the one we're most experienced with in use. But clean water is a resource, a limited resource that's in places. So in a dry desert region, you might want to look at an alternative heat exchanger. So I think some geothermal companies are proposing supercritical CO2 as a heat exchanger. Yeah.
Michael, you have.
Just quickly, are there any issues with the radiation levels at that depth? Interfering with the or being a pollutant?
Or radioactive?
Does any of the radiation at that level in the mantle come back?
I don't know for sure. I think it's fairly dilute. It'll probably have to be tested as you go down. One thing about ablating and sending the particulate out, it could be analyzed in real time at the surface at the well for the main constituents of the exhaust. You could have a portable mass spectrometer up there sampling, and once you start detecting nasty isotopes, you could stop and reconsider.
Thank you.
Any other questions? Well, I'm wondering. You seem to be competing in a way with your nuclear fusion buddies in this context. Do you see it as a competition now?
No, I can't knock fusion energy because I spent my career working on it. And I still am a rooter for them to succeed. We have the facility going up in Fort Devens there, Commonwealth Fusion, and they hope new superconducting magnets to start very soon. Pilot scale experiments out there, and I hope they're successful. I still think there's a lot of time needed to a practical plant, there will be issues with first generation fusion. Burning tritium can't be located near a populated area. So other second generations of fusion will be neutron free. But I think they have a little bit more to a practical plan. I think we have a possibility of putting power on the grid first, because there's so little extra engineering that needs to be conquered here. And so we're kind of competing, but in the long run, I think fusion energy is the ultimate source. But our director at the Planetary Fusion Center, Dennis White, is supportive to pursue this along with fusion, and so I think we're actually happy to see green energy come on in new and game-changing ways any way possible.
So what do you see as the timeline in respect to this technology?
We've had an optimistic timeline, but we had a little hiccup in Oak Ridge with the poor beam quality, and so we're still hopeful that within the next 5 years we'll be drilling deep wells. But I think there are some challenges, like I mentioned, the breakdown limits at atmospheric pressure and transmission through high pressure fluids at the kind of pressures we have underground through 1/10 to 3/10 gigapascal. So those have to be resolved, but I think there's solutions to that. Breakdown is only low at atmospheric pressure. When you go to vacuum, you don't have breakdown. When you go to super high pressure, you don't have breakdown either. So we're, on the planet's surface, we have a unique position that's not really that relevant to what we're after. So I think there'll be ways to engineer around that. And then supercritical fluid transmission, there are potentials to avoid induced dipole moments. For example, if you use an argon gas, I used that in my slide. Noble gas has no collision-induced dipole moments. So, so there are potential solutions, but they have to be shown experimentally. Yeah.
I know that other people here are also interested in this, which again is related to having a repository for nuclear waste. Do you think, have you ever looked at the possibility of using it in situ on the sites of nuclear power stations?
I haven't looked at it, but
so you could actually avoid transporting waste.
But I've thought about that too. That's true. If we could drill a deep well deep enough, it could be done on site more readily than mechanical drilling technology. I know DOE out of Idaho Labs had a plan to drill a test well in basalt, I think, North Dakota or South Dakota. Unfortunately, the local community wasn't told about that plan, and so that got canceled. But they would only be drilling, 4 or 5 kilometers. They're not talking about 20 kilometers. I mean, if we could go really deep, I think you could put even more distance between the biosphere and the core and get it really out of the way. I think there would be possibility for that.
What depth do you think that would be? Do you have any idea, or do we need to do work on that?
I mean, there were arguments that even at 6 kilometers, the conduction, even if you didn't have a perfectly sealed hole, would be so very, very low. But I don't know. I haven't done any study or anything to see what depth that would be. I've always, since some of our heat is obtained, well, most of geothermal heat, I believe, is the decay of long-lived radioactive isotopes, thorium, uranium, potassium. And I always thought that, if we could put our radioactive waste real deep and we get our geothermal deep, we'd just be adding to the geothermal energy that eventually we could mine. So dispose it in a way. I mean, if we're talking about depleting a fraction of a % of heat from the Earth, it would be nice to put more heat sources and to keep it hot. So throw the waste where it will help prolong the planet life. By the way, the thermal conductivity of Earth is so low that it's estimated that the Earth will cool down into a cold rock in 90 billion years. The sun's lifetime is only 4.5 billion years. Earth will be very hot long after the sun burns out. I mean, we could continue to mine heat and geothermal energy even after the sun burns out and continue civilization. Maybe we could power with the energy to move the planet to another sun. I don't know.
But I get another.
I'm going to give one last. Okay, Thomas, you got the last question.
Yeah, with such a huge potential benefit to this technology, and with it in mind that the Chinese are already on this road, why isn't the U.S. Energy Department managing this or taking such an interest to make sure that everything is being done currently on the road to putting this to use?
Well, I don't know how seriously the Chinese are on the road. There are laboratories, or the laboratory that I know of in Chengdu that's gained interest and has done an experiment. I had the VP of research come and visit me in my lab, and he showed me on the iPhone the melted rocks, and he offered me a position to work there. But my wife didn't want to move to China. But I don't know how serious their effort it is. They're only scratching the surface like we are right now. I know Quaise is doing a serious effort. They're going in a big way. And China, I don't think there's a real big effort that I know of. I mean, there is nice to see some experiments confirming our experiments. But they are challenges they have. I think we're in a position to solve them more quickly right now. And DOE is supporting. I mean, they're putting in ARPA-E, and Quaise has raised a lot of private support so far. And I don't know if there's a race between China and U.S. on this yet. I mean, I don't think it's generally in the drilling community, I don't think this is taken that seriously right now. So hopefully it'll change eventually.
I'm a bit surprised the Russians haven't tried to do it, considering they drilled the deepest hole, I think. Anyway, I really like to thank you very much for a wonderful talk. And I hope we'll be in touch as well, because I'd like to continue a little conversation about nuclear repositories. I'd like to thank you very much. And it's a wonderful talk. Thank you.
Okay, well, thank you. It was my pleasure.